Units and conversions going to be the topic of this lesson in my new general chemistry playlist. And we're going to talk about the metric system and SI units, which are smart. And we're going to contrast that with the American system, which is not so smart. We're going to talk about the different temperature scales and how to interconvert between those. We'll talk about density as well. And we're going to do a number of different conversions and dimensional analysis along the way. We're also going to talk about the most common mistakes students make and some of the more common errors made when doing conversions. So hopefully you're not one of the students making those errors. So let's dive in. And the first thing I'm going to do is talk about the metric system and SI units. And SI stands for the Système International. They're kind of the gatekeepers on units. And the metric system has got a number of units. We've got some that we call like kind of the base units and some that are kind of the derived units, which are combinations of these base units. And we're not going to learn them all in chemistry. So if you were taking a physics class, you would probably be on the hook for learning all of them. But in chemistry, there's some we use more commonly than others. And there's a couple that you'll find out that we more commonly use some other unit other than the actual SI unit. So I'll point those out when we get there. So with length, you want to deal with the meter. Just lowercase m for short here, the abbreviation. Mass, this one's important because the SI unit is the kilogram, but you're going to find out in chemistry, we are much more commonly going to be using just the plain old gram instead. So, but you should know that it's the kilogram that is actually the SI unit, even though we'll be using grams way more commonly in a chemistry class. All right, time, we've got seconds, temperature. So something we don't use very commonly outside of the realm of chemistry and physics and things of the sort is the Kelvin scale. So, but really handy scale, we call it the absolute scale because it actually has a true zero. So 0 degrees Celsius, like it's called zero, but notice there are negative temperatures. Well, on the Kelvin scale, there's no such thing as a negative temperature. When you get to zero, that's the complete absence of heat, and you can't go lower than that. The Celsius scale, you know, Mr. Celsius or Mr. Centigrade just said, look at water over there. It boils, I'm calling that 100, whatever temperature that happens at, and where it freezes, I'm calling that zero, and that's going to be the basis of my scale. Well, that's fantastic, but it's not a real zero, which turns out is important. Volume, it turns out, the SI unit, this is a derived unit now. It's derived from the unit of length, but it's length by length by length. So it turns out the SI unit is the meter cubed. And once again, we're not going to use this unit very often at all. We're much more commonly going to use the liter. So, and it turns out there are 1,000 liters in 1 meter cubed, and we're just way more commonly going to use liters. When we get to like talking about gases towards the end of this first semester topics, PV equals nRT. It's the ideal gas law, and we'll be talking about volumes almost always in liters. All right, energy and work. Turns out we commonly measure that in joules. If you take a look at you or your parents' most recent power bill, typically not going to be measuring the energy in joules there. Usually we use something called the kilowatt hour instead. Well, in chemistry here, we're going to be using the joule quite a bit. We probably won't be using the kilowatt hour in this class. And finally, pressure. The SI unit for pressure is the Pascal. And if you were taking a physics class, you would use this quite a bit. So, but in this class, you're probably not going to use it a whole lot, maybe not even at all, depending on who your professor or textbook is. And much more commonly, you're going to find out that we're going to use things like the atmosphere is probably the most common. So definitely not the SI unit, and it turns out there are, roughly 100,000 pascals is equal to 1 atmosphere. It's technically 101,325. Not a conversion you need to know at this stage of the game. But we'll use atmospheres way more common. We'll use other things like millimeters of mercury or torr as well, probably even more often than we'll actually use the Pascal. So, but these are the SI units. You probably just want to know each of these SI units. Again, these are not all of them. You know, it turns out there's an SI unit for luminosity, how bright a light is, and it's called the candela. And for the most part, we'll never use it in this class. So, but these are the ones you definitely should know. And again, couple key places where we're going to use much more prominently some other unit than the SI unit. Now, the next thing you should realize is the beauty of the metric system. And the reason I say beauty is everything's nice, lovely, round powers of 10. And we kind of identify those powers of 10 based on a certain prefix. So tera here means 10 to the 12th or 1 trillion. Giga means 10 to the 9th or 1 billion. So like when you hear like a terabyte or a terabyte is 1 trillion bytes and a gigabyte is 1 billion bytes. Mega, 10 to the 6th or a million. Kilo, 10 to the 3rd or 1,000. Centa, 10 to the negative 2 or 1/100th, 0.01. So just like 1 cent equals 1/100th of a dollar. So centa actually means 1/100th. And it's a little bit tricky because people are like, Chad, a centipede has 100 legs. You know, sort of. I mean, it does, but yeah. Milli actually means 1/1000th or 10 to the negative 3. Micro, 1/1 millionth or 10 to the negative 6. Nano, 1/1 billionth or 10 to the negative 9. Pico, 1/1 trillionth or 10 to the negative 12. Femto, 10 to the negative 15. Atto, 10 to the negative 18. So depending on who your professor is, they may not require you to know these last two or something like that. Or they might require you to know another one at the top or things of the sort. So, but I've tried to kind of be pretty comprehensive to cover just about any class. So, but these are typically the prefixes we make you memorize. And it's super important when we start doing conversions in a little bit here that you know what these prefixes mean. So make some flashcards or do what you need to do, but you need to memorize these. So because we're going to use them. And if you've memorized what they mean, it'll make the conversions a little bit easier. We'll find out there's two really ways you can do conversions. One of them is to use these prefixes as they are, which is what we're going to do. But it turns out there's a second way, and that's really frustrating because then we start, students will often start mixing and matching them. Professors sometimes present both and don't realize they're presenting two different ways of doing conversions. So we're going to present one way and use it exclusively, except for one example where I show you why there's another way and why we're not going to use it so that we don't get any confusion here. But we're going to use these lovely prefixes. Okay, I want to contrast this lovely set of powers of 10 with our lovely American system of units. And in our lovely American system of units, you might be like, well, there's 12 inches in 1 foot, and there's 3 feet in 1 yard, and there's 1,760 yards in a mile, or 5,280 feet in a mile. And all of a sudden, this gets really confusing, and we can talk about, cups and pints and quarts and gallons and, and there's not a nice, lovely rhyme or reason that's going to help you memorize it in every given context. So, but here, these lovely powers of 10 apply to any of these units and stuff like that. So a kilogram, well, kilo means 1,000. So a kilogram is 1,000 grams. A kilometer or kilometer is 1,000 meters. A kiloliter, which you're not going to hear that used too often, but a kiloliter would be 1,000 liters. And so it's nice because these prefixes apply to any unit. Whereas in our American system, if we're talking about length, we have a whole bunch of measurements for that. If we're talking about volume, we've got a whole bunch of different measurements for that. And they're not necessarily related, in any specific set way. And so it's really annoying. So if you just want to, chalk it up to you Americans, yeah, we're special. We know it. All right. So for those of you that aren't American and are using that metric system, props to you for being smart. All right, so we want to do some conversions now and use these. So I'm going to leave these lovely metric prefixes on the board so we can use them. But we're going to work a number of examples. And like I said in the intro here, we're going to show where students make the most common errors along the way as well. Let's dive in. All right, the first conversion we're going to do is converting 75 grams to milligrams right off the study guide here. And so if we want to go from grams to milligrams, first thing you got to realize that you're starting in the metric system, you're already in the metric system, and you're staying in the metric system. And that's a beautiful thing. As long as everything's within the metric system, it's all through lovely powers of 10. And so in this case, to go from grams to milligrams, we'll put grams on the bottom, we'll put milligrams on top. And a couple different ways you can actually approach this. So let's first look at what a milligram is. And a milli means 1/1000th. And the reason we say that is because we're going to say that 1 milligram equals 1/1000th or 0.001 grams. And another way of writing 0.001 is 10 to the negative 3. And that's where that power of 10 comes from. So we can say that 1 milligram equals 10 to the negative 3 grams. So, and you can use that equality there as your conversion factor. We could put a 1 milligram here equals 10 to the negative 3 milligrams, and we're going to get the right answer. Life is good. Our dimensional analysis is a term we often use, and it just means make your units cancel and stuff. And so this gram is going to cancel this gram, 1 in the numerator, 1 in the denominator, and we'll come out with our answer in milligrams. And when you divide by 10 to the negative 3, that's no different than multiplying by 10 to the 3. And so in this case, we're going to get 75,000 milligrams. And if I cared about sig figs, and I'm not super concerned, but I'm going to try and actually, pay attention to that. 2 sig figs here, 2 sig figs here. These zeros are not significant. So, and that would be one way of accomplishing this. And this is the standard way we're going to do this. But even though 1 milligram is equal to 1/1000th of a gram, well, because 1 little milligram is 1/1000th of an entire gram, you could also say that you can equate that there are 1,000 milligrams in 1 gram. So, and 1,000 is the same thing as 10 to the positive 3. And so you could say that 1 gram equals 10 to the third grams. And you could also use this equality to do the conversion as well. And so instead of, we're still going to need milligrams on top and grams on bottom so that the dimensional analysis works out, the units cancel. But now it would be 1 gram is equal to 10 to the third milligrams. So hopefully what you see here is that a conversion factor here is just an equality between different units. That's what it always is. And so as long as you can express a numerical value of one set of units and another set of units, you can use that as a conversion factor. And so notice here, we said that dividing by 10 to the negative 3, well, that's no different than multiplying by 10 to the positive 3, which is what we'll end up doing in this case. And so it's going to lead to the same answer. It would still give us 75,000 milligrams. So, however, this one has 10 to the third in it, which is not what milli ultimately means. And so there's two ways to do this. And the way we're always going to do this is whichever of your lovely units has a prefix, that's where you're going to put the 1. So whichever one does not have a prefix, that's where the power of 10 is going to go. Notice it's exactly backwards from what we're doing down here. And so the truth is, when I'm doing conversions in my head, sometimes I do them this way, and I've been doing this a long time and stuff. I'm never going to present it that way from here on out. I'm going to present it in such a way that we always use the exact power of 10 that the given prefix means. That's the way this is going to work. And again, the way this always works is your unit with the prefix on it is always going to get the number 1. So, and your base unit is always going to get the power of 10 for any metric conversion. Okay, so that's our first lovely conversion here. So we'll move right along here. And the next one, 17.1 meters, and we want to convert this to feet. And we have our first problem. So meters is in the metric system, feet is in our lovely American system. And so we're going to have to cross over from one system to another. And to cross over from one system to another, you're going to need a conversion factor. And we typically don't make students memorize these, although it's fair game if a professor wants to do that. So, but most of the time that's not the case. And so if I want you to cross over from one system to another, I have to actually provide you with a crossover, that's what I call it anyways, a crossover conversion factor. In this case, the one I provide is 1 inch equals 2.54 centimeters. That's the one I provided. Now, I could have provided others, and the truth is, if you were converting, meters to feet in everyday life, you'd just pull out your phone and you'd Google it, and life would be good. So, but obviously, that's not going to be acceptable on your exam, so you do have to know how to do this, and this is the one I'm providing you with. And based on what I provide you, in this case, we're starting out with the metric, which means if I want to cross over and get into the American system, I have to do it through the centimeter. And so I'm in meters now. I got to get to centimeters because that centimeters is my key into the American system by way of inches. And so first thing we'll do is we'll convert from meters to centimeters. So we'll need meters on the bottom, centimeters on top. And we'll just set up the units first. This is kind of the process of dimensional analysis, setting up the units. And that'll get the meters to cancel. So, but then I can convert centimeters to inches, and this is where we cross over systems. I'll put centimeters on the bottom, inches on top, so that the centimeters cancel. So, and again, ultimately in this case, we want to end up in feet, and we know how to convert inches to feet. There are 12 inches in a foot. And so inches on bottom to make them cancel, feet here, and that'll get the inches to cancel, and we'll be left with an answer in feet. And now we can go back and fill in the numbers. Now in the first part, this is just a metric conversion. And once again, whichever unit has a prefix, and notice centimeter has the centa prefix on it, that's where the number 1 goes. And then your unit without the prefix, in this case just the plain old meter, that's where the power of 10 goes. And centa means 1/100th, or 10 to the negative 2. So we'll put that in there. And then inches to centimeters, again, that's the crossover between the American and metric systems, and that's got to be provided, or again, your professor technically could make you memorize a few of those, but usually it's something that's going to be given to you, and I gave it to you right here. And so in this case, we just plug these numbers in. 1 inch is equal to 2.54 centimeters. And then finally, 1 foot is 12 inches. And For those of you that are not from the US but might be taking general chemistry in the US, we do expect you to know a few things, like especially this one, that 1 foot is equal to 12 inches. Now, whether or not we expect you to know that there's 5,280 feet in a mile, maybe not. In fact, a lot of American students don't know that. So, but this one we do expect you to know. So 1 foot equals 12 inches, and probably that there's 3 feet in a yard, probably too, as far as length goes, that you should probably know. Cool, but this is the whole thing, and let's grab a calculator here. I had a calculator, my son stole it. All right, so here we've got 17.1 divided by 10 to the negative 2, and for 10 to the negative 2, if you've got a nice, lovely scientific calculator, I'm going to write that as 1e, which means times 10 to the power of negative 2. One of the big mistakes students make is instead of saying 1e to the negative 2, they do 10e to the negative 2. So that means 10 times 10 to the negative 2, but this is the same thing as 1 times 10 to the negative 2. Anything times 1 is itself. So 10 to the negative 2 is the same as 10 to the negative 2 times 1. All right, so 17.1 divided by 1e to the negative 2. And I can put these all in parentheses, or I can just separately divide them out. It works either way. So, but we're also dividing by 2.54 and also dividing by 12. And we get 56.10. Feet. So, but now let's go back and worry about those sig figs. And we've got 3 sig figs in the original number. So, and this is where we didn't really address this initially. So, but much more important here is how do we figure out how many sig figs here? And you might be like, well, Chad, okay, we learned sig figs in the last lesson, and all we're doing is multiplying and dividing, so it's just whichever number has the lowest sig figs. Well, sort of. There's something special about units and conversions. So it turns out your sig figs are never, the proper number of sig figs is never going to come from your conversion factors, because they're not like rough approximations. It's not like there's close to 12 inches in 1 foot. There's close to 12 inches in a foot. No, this is exact. There is, 12.00000 inches in 1.000 feet, and you can say 000 is forever. It's exact. This actually represents an infinite number of sig figs in the conversion factor. 1 inch, we're going to take it as meaning 1 inch is exactly equal to 2.54 centimeters with zeros forever, an infinite number of sig figs. Same thing here. So this is exact. 1 centimeter is 10 to the negative 2 meters exactly with an infinite number of sig figs. And so if all our conversion factors have an infinite number of sig figs, well, then we're going to have to get it from the first one. And with multiplication division, it's usually the lowest number of sig figs in whatever numbers you're multiplying dividing, except with conversions, never from the conversion factor. So it's really all got to come from him. He's the only number that's not a conversion factor, and he's got 3 sig figs. So now we need to end up with 3 sig figs. And so in this case, we need to round it either up or down at the 1 there. And because the following digit is a 0, we'll round down and just keep it a 1 and end up with 56.1 feet. Okay, cool. So next thing we're going to find out is the other place where students often make common mistakes. We saw the first one already, and common errors occur, when instead of using what these prefixes actually mean, you use how many of each of these is in the base unit or something like that. And again, I'm never going to present it that way from here on out throughout the entire course. But here's the other place. When you're dealing with either area or volume and using units of either length squared or length cubed respectively, conversions get a little bit tricky. And so in this case, I'm asking you to convert 0.00348 meters cubed to centimeters cubed. And so in this case, what students often do is they go meters, then they go centimeters, and they're like, oh yeah, it's all about powers of 10. And again, whichever one is the base unit gets the 1, and whichever one has the prefix gets the 1, and whichever is the base unit gets the power of 10, which means 10 to the negative 2, and 1 centimeter is indeed equal to 10 to the negative 2 meters. But that's not what we need. In this case, notice it's meters cubed. If this is just meters, those aren't going to cancel all out. Meters cubed divided by meters is meters squared, not, they didn't cancel completely. And so what we actually need to do here is cube the entire conversion factor. Look at what this ends up looking like. So 0.00348 meters cubed times 1 cubed centimeter cubed. It cubes the 1 and the unit as well. Same thing here, 10 to the negative 2 cubed meters cubed. And so that cube up there not only cubes the units, but it cubes the numbers as well. And so a lot of students are like, I didn't see this coming and stuff like this. And so I'm going to use one other example before we actually finish solving this. And we'll need a little bit of room here. So, but if I say I've got an area of 1 foot squared, or 1 square foot, and I ask students typically, oh, how many square inches is that? And they're like, well, 12 square inches, Chad, except that it's not. Notice if I have a square that is 1 foot by 1 foot, well, then the area is just going to equal length times width here, and 1 foot times 1 foot is equal to 1 foot squared. Okay, no big deal. But notice, what if I'd given those dimensions instead of in feet, I'd given them in inches to begin with? Well, 1 foot equals 12 inches. And up here, same thing, 1 foot equals 12 inches. And if I multiply 12 inches times 12 inches, I don't get 12 inches squared. I get 144 inches squared. And so that's why you can't just use the, 1 foot is 12 inches. That's true, but 1 foot squared is not 12 inches squared. It's 12 squared inches squared, or 144 inches squared. And so that's what we're doing down here. We're using kind of the standard conversion factor, but if it's units cubed, we've got to cube it. If it was units squared, we'd have to square it, and so on and so forth. And again, that not only cubes, in this case, the units, it cubes the numerical values as well. And so instead of dividing by 10 to the negative 2, we're actually dividing by 10 to the negative 2 cubed, which is 10 to the negative 6. And so that's going to move this over 6 decimal places. So we got 1, 2, 3, 4, 5, 6. We'll have to add an extra 0 there. And so in this case, we're going to get 3480 centimeters cubed. And if we go back to sig figs again, starting with a number with zeros, they're never significant. And so it's just 3 sig figs. And in this case, this 0 is not significant, so we have 3 sig figs, and we're actually good. Nothing more we need to do. That is our lovely answer. But that is the other place where we see a huge common error, either with units for area that are like meters squared, or units of volume that are like meters cubed, and doing a conversion there. So don't get tripped up on this one. All right, so now we got to deal with temperature here. And if you are from the US, you probably use Fahrenheit more commonly than anything else. And I live in Arizona, and a nice hot summer day might be on the order of like 110 degrees Fahrenheit, which is hot. And if you're not familiar with the scale and you much more commonly use the Celsius scale, it probably sounds hotter than it is, but it's still plenty hot. But on the Celsius scale, that might be, in the upper 30s or lower 40s in terms of centigrade, which is, plenty hot. And I'm sure for most of you would agree. But for us, for those in the US, they're probably like, I have no idea what that would be on the Celsius scale and things of this sort. But there are a couple temperatures that most students can equate the two on. And so often people know the freezing point of water is 0 degrees Celsius or 32 degrees Fahrenheit. And they might know the boiling point of water. Boiling point of water is 100 degrees Celsius, and that's 212 degrees Fahrenheit. So, and one convenient thing here as well, it turns out that negative 40 degrees Celsius is negative 40 degrees Fahrenheit. That's the one temperature they have in common. And so what's nice is if you forget either one of these lovely formula that give you the conversions between Celsius and Fahrenheit, you can actually derive them. You can actually view any two of these points as being 2 points on a line, and you could find the slope of that line. And depending on which you put on that axis, that slope might either be 5/9 or 9/5 and things of this sort. So you could actually derive these equations if you had to. Now, we'll tell you that you're going to be converting between Celsius and Fahrenheit in all likelihood way less commonly, maybe never, but way less commonly than you're going to be converting between Kelvin and degrees Celsius instead. So this is the really important one, but we'll do an example of both here. And so in this case, I'm giving you 10 degrees Celsius, and I first want you to convert that into both Kelvin and Fahrenheit. And we'll definitely start with Kelvin here. In this case, Kelvin's nice because all you do is you take your Celsius and you add 273. If you wanted to go from Kelvin to Celsius, then you would subtract 273. And so in this case, all we've got to do is go plus 273, and that's going to get us 283 Kelvin. And notice we don't call it degrees Kelvin, it's just 283 Kelvin. All right, so what if we want to take that 10 degrees Celsius and convert it into Fahrenheit? Well, to convert it into Fahrenheit, we do this guy right here. And so we take and multiply it by 9/5, and then add 32. And notice 9/5, the 5 and the 10 will cancel, giving us a 2 right there and a 1 right there. And so we'd have 9 times 2 is 18, plus 32 is going to give us 40. Not degrees Celsius. How about 40 degrees Fahrenheit? And notice at 10 degrees Celsius, we're a little above freezing, and 40 degrees Fahrenheit, notice freezing again was 32 Fahrenheit. So yeah, we're a little above freezing, and that makes sense. Cool. And essentially, we haven't actually converted from Kelvin to Celsius or from Fahrenheit to Celsius, but it would just be using the inverse of the first formula or this other formula here instead. But that's kind of how it works. And again, Kelvin is the SI unit, and we're going to find out there's certain applications where we have to use Kelvin. It's what we call an absolute scale, and that just means it has a real zero that you can't get lower than. Whereas on the Celsius scale, again, Mr. Celsius or Mr. Centigrade just said, oh, look at that, water freezes at that temperature, I'm calling that my zero. But you can go lower than that. So absolute zero Kelvin refers to the complete absence of heat. All right, we're going to finish this lesson off talking about density. And you might recall density in the first lesson of the chapter. We talked about it as being an intensive property. It means that regardless of how big or small your sample is, the density is going to be the same for that sample. And it turns out because of that, we can use density to actually identify what certain substances are in some cases. And, in fact, in the precious metals circuit, you can spot fake gold or fake silver because if they haven't done a really good job, it probably isn't going to have anywhere close to the same density as real gold or real silver and things of this sort. But it turns out density is the ratio of mass divided by volume. And you should just treat this as an algebra equation that has 3 variables in it. And if I give you 2 of the variables, you can solve for the third. If I give you the mass and volume, you can solve for the density. If I give you the density and volume, you can solve for the mass. If I give you the density and mass, you can solve for the volume. And you might get some calculations with this. Now, notice I wrote it a little bit different here, and this is the Greek letter rho. And it turns out this is actually the proper variable we use for density. And you'll use this ubiquitously in a physics class. But in chemistry, for whatever reason, we're rebels a little bit, and we don't want to use the official one. And so you may see it this way in your text, but oftentimes in chemistry, we'll use the lowercase d instead. And that's most likely. But if you see it as the Greek letter lowercase rho, that is the official variable for density, and probably the one that we should use. We just typically don't. But in physics, that's probably what you'll see. So I just want to make sure you'd seen that just in case. All right, so first question on your handout there involving density is, a cube with 2.00 centimeter edges weighs 12.0 grams. What is its density? So let's write this correctly. 2.00 centimeter edges weighs 12.0 grams. And in this case, what is its density? Well, you got to know that the volume of a cube is side times side times side, which in this case would be 2 times 2 times 2, which is 8 cubic centimeters. And so density equals mass over volume, which in this case, we're given the mass 12.0 grams over 8.00 cubic centimeters, 2 by 2 by 2. In this case, we got 3 sig figs on top, 3 sig figs on bottom, and so our answer in this case should come out in 3 sig figs with division going on here as well. And 12 divided by 8, so we could reduce that down, in fact, to 3 over 2, which is 1.5, and we'll just tack on an extra 0 to get that third sig fig, 1.5, and the units would be grams per cubic centimeter. Cool, and that would be our density in this case. So we've just done a calculation. Again, treat this as an equation with 3 variables. If you know 2, you can calculate the third, exactly what I had you do here. Now, the next question says, how much would a cube of this same substance with 3.00 centimeter edges weigh? So if we had a little bit larger cube now, 3.00 centimeters, how much would it weigh? And the key is, because it's the same substance, it's going to have the same density. Again, it's an intensive property. And so in this case, now we're being asked for how much is it going to weigh. And so we just rearrange the equation here, and if we multiply both sides by volume, we'd get mass equals density times volume, and that's essentially what we're going to be doing here. So in this case, the density we know, we just solved for it. It's 1.50 grams per cubic centimeter. So the volume is what we don't know, but again, this is a cube, and it's just side by side by side, so 3 times 3 times 3, which is 27.0 centimeters cubed. And notice your centimeters cubed are going to cancel, and your answer is going to come out in grams, just like it should. Great time to pull out a calculator, but you probably could do this in your head because half of 27 is like 13 and a half, and so you'd add 27 plus an extra half of that, to multiply by 1.5, but we'll just use our calculator. So 1.5 times 27 gets us 40.5, that extra 13.5 plus that 27. So in this case comes out to 40.5, and that's in grams. And again, we wanted 3 sig figs. Both our numbers have 3 sig figs. Well, it has 3 sig figs. So we didn't have to add any more zeros to this or anything like that around in any crazy way. It just comes out to 40.5 grams. Now, as I mentioned at the beginning of this lesson, this is part of my new general chemistry playlist. I'll be releasing these lessons weekly throughout the entire school year, so if you want to be notified every time I post a new one, subscribe to the channel and click the bell notification. However, if you want to make sure that you're the only one in your class who gets to see this lesson, then do not like and do not share this video, because that would tell YouTube to make sure it gets a broad audience. And if that's exactly what you don't want to happen, then don't like and don't share this video. I've also got this course embedded as a free course on chadsprep.com, and with every video I put pretty much everything that's on the study guides on the page to go with it as a companion to it. So I'll leave the exact link to this particular lesson in the description below. And I also just want to make you aware of my general chemistry master course as part of a premium subscription on chadsprep.com. And in that master course, in addition to the videos and in addition to the study guides, there are tons and tons of practice. And for a lot of that practice, it also comes not just with a really good written solution, but with a video solution. I really want students to walk away understanding exactly why they got a problem right or wrong if they're not sure. Now, in addition to tons of practice, there are final exam reviews and practice final exams and chapter tests, things of this sort as well. And what's nice is the first couple of chapters are all available as part of a free trial, so you can check out the quizzes for this lesson, as well as the entire first couple of chapters absolutely free. Happy studying.